Okay, let's roll. A few comments about the project. Um, okay, it's due next Wednesday. I'm sorry, I this Wednesday. This Wednesday. Next Wednesday is just coming up in 2 days, right? That's the next Wednesday, right? Okay. I really don't want to. I mean, I understand some of you have 150 projects or exams and stuff, but it's a slippery slope, right? If we delay this, then the homework is delayed, and et cetera, et cetera. And it's kind of I've gone down that path before, and it just doesn't work. Any question? Would you mind?
For the area of the drains and the shores in the PD, if we include that and it doesn't really make any difference, can we just don't really care about it?
Doesn't make any difference.
Well, it does, but it's not significant.
10%. If it anything less than 10% doesn't matter, right? So make sure you got your units right. If you get your units wrong, you can be off by a lot. But
The size of my transistor is really small.
Yeah.
Pretty much right at the minimum. So
Yeah, so it may not matter at all. So that's but it, very no. If it doesn't make any difference, I mean, okay. So in your write-up, I guess what you're worried about, I suppose. Okay, you need to calculate the lowest frequency pole. Do that as well as you can. Um, if make the right approximations. If things are less than 10%, you can ignore it. I mean, that's just fine, right? Say if you have some reason why you can ignore it. So I guess the write-ups will be, hopefully this is consistent with what's on the website, is 2 pages of text. You can have 1 page of schematic and transistor sizes, I guess. And you don't need to do hand calculations. You just need to put them down. The TAs wanted the transistor sizes and voltages, I guess, so they can make sure that your circuit's really working or something. I don't know, but they asked for that. So, okay, so 2 pages. So on that 1 page, it has your schematic and 1 page, yeah, 3 pages altogether. Right, right. You don't need to do for hand calculations of the lowest frequency pole. Yeah, including that. Now put that on somewhere. No more than 3 pages. Okay.
Question. How to calculate the zero? Is there any trick to calculate the zeros?
How to calculate the zeros? Is that setting your 3 dB point?
For the guideline, is that you need to calculate for important poles and zeros.
Well, the important ones would be ones that set the 3 dB frequency, right? And so if it doesn't set the 3 dB frequency or have some effect on that, then you don't have to worry about it. Okay? They're difficult to calculate, yeah.
I just want to make sure the only test bench we need to pass is a test bench that is posted online. Like there won't be any secret test bench that you guys impose on us.
No. You should have all the test benches. Sorry they didn't get out earlier. That won't happen next time. But all the test benches that we will use for grading will be ones that you guys test against. So, okay. Now, there's something you okay, test benches. You should understand how those test benches work. I mean, those are just convenient ways for you to sort of evaluate. It's convenient ways for us to evaluate whether your circuit's meeting the specifications. But it's also good for you in the long run to learn how to write those kind of test benches so you can do your own test benches for if you have something besides doing homework at 140, right? If you want to do something on your own, you should learn how to do that. I will ask the TAs to you should be able to understand how those test benches work. All right. I mean, if you don't, let's talk about it. Okay. Right. And yeah.
Since for this project we're looking at about 10 different stages, what's the easy way to pin down to which node we're actually looking at for the lowest frequency of pole?
How do you compare what's happening in SPICE, you mean, to what you're actually measuring, what you're calculating? Not easy. I think you go in and you look for the node that seems like the one that's going to have the highest resistance associated with the highest capacitance, right? And it's no easy way to do that. Yeah. But I think you should know roughly what's going on, right? I mean, most of them will probably be very similar, okay? And you can pretty get a good estimate. All of these are going to be about the same. Okay, I know what there are. This one, driving the output stage, that's really high. Okay, that may be likely. But it's the input stage that you have to worry about. Okay, so I think there's.
If you have like about 3 or 4 different repair stages, and all the size of the transistors are the same, so which means that the pole is going to be pretty much similar to each other. So do we have to do all the poles or just do one and the rest of it are similar?
Yeah, if you could make some argument that these are all about the same resistance and current and capacitance. I mean, I don't need to see duplicate.
You don't need to see the same poles that's being calculated over and over again, right?
I think if you can say they're all the same and right on top of each other or something like that, that's fine, right? What?
Just one page calculation.
You can't do much anyway. Exactly right. I mean, I don't. I just. What am I after? What I'm after is that you understand where the lowest frequency pole is, and that you did a hand calculation that roughly verified that you understood where it was. That's what I'm after. If you can make that happen, if it's a combination of several poles that are right on top of each other, and you have to make that argument, these are all about the same, that's fine too. Okay, so that's what I'm after. So let's say, so learn how the test benches work. If something's getting pretty weird, if you're getting some strange results, what you also ought to run is a frequency response sweep. Your response should look, something like this. It should go, flat and then fall off, and this should be the 3 dB frequency that you get from the test bench. If you've done something strange in your circuit and you get some, weirdness going on, like some sort of feedback thing that's causing instability, you might be able to fool the test bench. Okay, the test bench may give. I'm not sure how it's calculating 3 dB frequency. I haven't actually looked at it myself. Be sure you're not doing this. I guess maybe a question about secret tests. But all right, we do want you to have a circuit that's working, and just because the test bench is being fooled doesn't mean that you've done a good job, right? Okay, so if you start getting strange results that don't seem to make sense at all, you better check to make sure that you actually do have not some instability or something in your circuit. You shouldn't get instability unless you're doing some sort of feedback thing or something like that. Is there anything else I want to say? Oh, yeah. Okay, in office hours today, I did say something, and I want to retract it to a certain extent. Someone asked, well, if I do something that takes more area and's not a good design practice, is that something I shouldn't do? Yeah, you probably shouldn't do it. I was going to say, what's unfair, and I understand this is unfair, if we sort of, in the figure of merit, give you, like, we have no area constraint this time. So you start doing things that just use tons of area. Is that a really bad design? Yeah, it is a bad design. You shouldn't use tons of area, even though the figure of merit doesn't say it. And I was going to say something like, I wouldn't count against that, but I would like you to know, I mean, certainly if you start eating up lots of area with something, if you can explain, if you say something like, well, I didn't do the simplest possible thing, like was, use something that takes a lot of area. I did this because it takes less area, even though the figure of merit didn't require it. Okay, that makes me feel good that you understand what's going on. Okay, that's really what I'm after, is that you understand some interesting things about design, right? And you can, in your little 2-page write-up, you say things like that. That would be useful to me. Okay, I use this circuit because it had less area, even though the figure of merit didn't require it. That'd be worthwhile. it's a little, I understand it's a little nebulous. That's kind of what design projects are all about. It's hard to figure out how you grade them. I mean, that's why we, have the specifications and so on. Right? Yeah.
But you don't really know how much your 3dB should be though, and like how you really know even you have more area, and then you increase your 3dB, but then you know how much should you increase or
Yeah. Obviously, this is not. I was going to say, if you do something that takes a lot of area, that's just fine because we didn't include it in the figure of merit, and it won't be counted against you in any big way, and that's true. Okay. I'm just saying if you do make some comments about how you did some things to reduce area, it'll count a very small amount. Okay. All right. Not very much, right? Because I didn't include it in the figure of merit. So I mean, we gave you the figure of merit. That's what we wanted you to optimize. That's what the best design will be. But in your write-up, if you just talk about what a good design is, that will give you a very, very small increment. Okay, right. Maybe it compensates for some things you say that aren't correct. How's that? Maybe it's okay. Right, so, okay, is that helpful? Probably not. Yeah. Okay. What I want you to do, bottom line. I'd like to see in the write-up that you understand what your circuit does and why it does it and why you designed the way you did. That's what I'm really looking for in the write-up. Okay, that's the most important thing. If you can keep that in mind, that's what will be good. All right, with that clear-cut set of guidelines, any comments, questions, anything like that? So, project due this Wednesday. New homework coming out this Wednesday to next Wednesday, feedback. Next homework will be stability, then the final project. So we're getting toward the end. Questions? Okay, feedback. All right, last lecture, what we did was we analyzed a circuit without the loading effects. With the loading effects, what I mean by that is if we take this schematic form of feedback. I mean, this is the basic amplifier in this direction, right? And this is, and in this direction we have the feedback, okay? Notice what I have down here. I have basically an ideal circuit for the feedback network. I mean, there's no output resistance and there's no input resistance. Well, in actual fact, the feedback network will provide loading on the basic amplifier, okay? I mean, in other words, if I just draw, if I take a typical amplifier like this that has an input resistance and an output resistance and a voltage gain, right? AV times V error, and this is V error across here, and here's R out, and here's R in. And I have a feedback network. Here's Vn. This is R1 and R2. You can see that this amplifier has to drive this feedback network. I mean, it's just like we put a load off the output, right? You got your 1K ohm resistor. You know what that load resistor does. It makes your amplifier, you have to worry about this output resistance of the amplifier in order to drive this load resistor. Well, this feedback network is part of the load, right? It has to drive this load. If I'd made this R2 and R1 for this little series shunt feedback network, which you know what it is, I'm sure, if I made this 5 ohms and this 1 ohm, this amplifier is going to have, and this R out is equal to 1K ohm, this circuit's going to have a real tough time working, right? What's going to happen? This output resistance is very high compared to these R1 and R2. So looking into here, we'll see an effective resistance associated with this feedback network. The question is, what is that resistance that we see looking into here? Well, it depends what we do on this side. Okay? Now remember, the feedback network is operating in this direction. So this is feeding back a voltage. Okay, this is a question to you. Is this feeding back a voltage or a current? Is a voltage or a current being fed back in this network? Voltage, right. How does he figure that out? It's in series, right? This is series feedback, right? Series. Okay, right. The voltage, here's the input. Here's the feedback voltage. They're in series with each other. Right? So this is series feedback. How are we sensing something? This is V out. Our feedback network's connected right to the output voltage. That's in shunt, right? So this is series shunt feedback. So we're sensing a voltage and feeding back a voltage. Feeding back a voltage in series with the input here. What will we assume about this resistance looking up in this direction when I calculate this feedback voltage? Do I assume it to be short, or do I assume it be an open? Open, right? Series open, shunt short, okay, right? So it just assumes it's an open. Why is that? I'll give you a little reason why this is true. Why this appears to be an open, okay? Here's a little insight into how feedback works. It's fairly straightforward to look here. What is this feedback doing? It's driving V error to be small, right? V error, what we're doing will be equal to V in, if you remember, divided by 1 plus the loop gain. We calculated that, a couple days ago, right? So V error, that's what negative feedback does. It makes V error go down. It's trying to drive that V error voltage to 0. If this voltage is going to 0, what is the current that we're seeing into here? If V error is going to 0, the current here is V error divided by Rn. So this is kind of I in some sense, right? If this is I in. So looking up into here, we're seeing the input current, I in. If V error is going to 0, what's that current doing? It's going to 0. If that current's going to 0 up in this lead, what does that look like as far as we're concerned? An open circuit, right? So it's the feedback voltage, driving this error voltage to 0 across this input resistance that's causing this to look like an open circuit. So sure enough, we make this open circuit. When we try to do our analysis of the loading effect looking into the output. Get that? So in other words, looking into the output side here, we assume this is an open circuit. So what is the resistance that we will see from the point of view of the output of this basic amplifier? It's going to be R1 plus R2, right? Because this is open circuit looking up into that direction. So in other words, I can redraw this amplifier so it looks like this. As far as the loading effects are concerned, I'm not worrying about the feedback right now. I'm just worrying about the loading effects. So on this output, I have an R1 plus R2 to ground, and that's open circuit that way. Okay? From the input side, okay, this is V in. This is R in. We have to worry, there's loading going on the input side as well. And why is that? That's because we have V in here, we have an R in, let's say in general. Let's say it's not open circuit. Let's say it's for this, whatever circuit we're working with right now, the more general case. The V in is going to be divided between R in and the resistance looking in this direction, right? In other words, I'm going to have, here's V in, the voltage across here, and this is V out, and this is V error. V out equals A times V error. Now AV, and I'll call it prime because there's some voltage division going on in this output, because the output has this R out, right? Let's make this little R out. Make this little, I'm sorry. There's an output resistance R0, which is being voltage there's going to be if we have a load here, not all of, this is AV times V in, there's going to be some voltage division going on in this output, right? So we don't see all of V out exactly equal to AV times V in. It's going to be AV prime, where AV prime takes care of this voltage divider, right? I mean, AV prime will be equal to AV, which is the open circuit output voltage, times V in, times the voltage divider. And that's going to be equal to R0, R1 plus R2 over R0 plus R1 plus R2, right? This is just the voltage divider between the internal voltage gain, the output resistance, can you read that? R0. Output resistance R0 and R1 and R2. As R1 and R2 get really small, of course you get a lot of loading effects and the output voltage goes down. So that's the loading on the output. On the input, looking into here, this is the R, make a capital, R out of the feedback network. Looking into here, this was R in of the feedback network. R in of the feedback network we decided was equal to R1 plus R2. The R out of the feedback network is looking in this direction. We have to worry about what do we do with this the input side of the feedback network. Do we short it or do we leave it open? Who can tell me? Short. How do you know it's short? Shunt, short. Good. Okay, that's one way. Okay. What's the other reason? Okay. Wanna try it? What's the microphone?
I think because it's like a voltage source.
Yeah, thanks. Exactly. We got it out there just before you got squeeched out, right? It's a voltage source. Right. This is being driven from a voltage source. A voltage source, an ideal voltage source. You assume it's the sort of ideal input. You assume it's sort of the ideal output of the feedback network when you figure out these loading effects. We're just doing two-port analysis here in effect, right? And that's what we always do when we do two ports. So it's being driven from a voltage source. That's like independent voltage source in some sense. We set that to 0. That's like a short circuit. So in other words, as far as looking at the output here, we will short the input. And the mnemonic is shunt equals short, right? Okay, so we short this side. So what is the resistance we see looking from the output? We see an R1 to ground. We see an R2 to ground. So therefore, we have R1 in parallel with R2. So now V air is not exactly equal to V in, right? Because what's going to happen is we're going to have a voltage division of V in. If R1 was equal to 0, there'd be no loading and V air would equal to V in. But now that we have a finite value of R1 and R2, we'll have a voltage division between that and Rn. So V air is equal to Rn over R1 in parallel with R2 plus Rn times Vn. So we lose some of the input across this input loading. We lose some of the output across this output loading. So we lose on both sides. So this is what I call including the loading effects of the feedback network. When we did the analysis last lecture, I set this to 0 and I set this to open. All right? And I didn't include those effects. Now I'm including them. And that's what you always have to do. The reason I did it the other way last time was just to not add too many new things all at the same time. Okay, so this is how you have to always work the problems, including the effects of the feedback network. Okay. So how do we do it? What we're going to do, in order to be able to use the same expressions that we had last lecture, okay, I'm going to create a new basic amplifier that includes all of this loading effects. Okay, that's going to be my strategy. I'll make a new basic amplifier that includes all this loading. So how do I do that? Let me redraw this so it's a little bit cleaner. So here was our old basic amplifier. Has R in. It goes down to R1 in parallel with R2. And here's the output. And this is AV times V air, and this is V air, and this is R out. And this is our output, V out. And here is our R1 plus R2. So I want to include all of this, and I want to make a new basic amplifier out of it. Okay? I'll keep, so I want it to look like this. So I'm going to have a new R out prime. I'm going to have a new AV prime times V air. Okay. Prime in a sense, right? I'm going to have a new Rn prime. And here's my new V air prime. So I want to redefine, or I can call this Vn. Let me make this Vn. Yeah. What did I do in the notes? What did I do in the notes? What did I do in the notes? V air prime. Okay. I call it V air prime. Okay. Now, so how do I relate? So this is now a basic amplifier just like we had before. After I get the answers from this, I can go back to my old expressions that I had last week, right? I mean, R out of this circuit with the feedback. Now, this is my old, the expressions I had for R out. This is with feedback. Closed loop feedback will be R out prime, like divided by 1 plus T prime. T prime will be equal to A prime times F. Okay, F is the feedback factor. Right? So I'll create a whole new set of, have a similar formula for Rn, right? It'll be Rn, the new Rn prime times 1 plus T, right? So let me just write that down. So there'll be an Rn, which will be Rn prime times 1 plus T prime, right? Okay, so so if I can get these new values, I can just plug in my same old formulas. What is R out prime going to be? Well, I need to do basically the Thevenin equivalent of this output circuit. Looking into here, what's the effective output resistance? Well, you set the independent sources to 0, set this to 0, you set this to 0. So looking into here, what am I going to see? I'll see R0, the old basic amplifier output resistance, in parallel with R1 plus R2. Okay. Let's do Rn prime. Rn prime is the input resistance I see looking into here, all of the input resistance. So what's it going to be? It's going to be Rn plus R1 in parallel with R2. That's my new input resistance, which goes into here. And what is my new AV prime, or my product AV prime times V error prime? Okay. Well, let me. Question? Yeah.
So the reason you're able to split those two up and then put it to ground is because from like the input side, it looks like it'll be a short on the other end,
And there's an open on the other end from the output side. Exactly right.
sorry.
Exactly. Yeah. What I'm trying to do now is just figure out the effective loading on the input and output side, and I do that because I'm kind of breaking the feedback network in a sense, right? What I'm able to do here is I can know what this is going to look like from this side, And I know what this is going to look like from this side. And so that's the facts that I'm using to break this feedback network. Okay. So I've got the new R out prime, I got the new Rn prime, and now I need to get the new AV prime times V error prime. So V, okay, so AV prime, the output, I can see is being voltage divided between this thing here, so I have a V prime is going to be equal to AV times R1 plus R2 over R0 plus R1 plus R2. And V error prime is going to be equal to V error so what I'm doing basically is calling this V in equal to my new V error prime, because I want to have, it's the voltage I'm applying across this whole network, okay? So V error prime is equal to, actually I have to reverse here for a second. From this divider right here, I can see that V error, did I do that already? No. V error is equal to V error prime times Rn over Rn plus R1 in parallel with R2, right? So I'm calling this whole voltage across here equal to the input to my basic amplifier. Before I was calling, so let's call that V error prime. Relationship between V error and V error prime is this right here. I want to solve for V error prime, so I end up with V error prime equals V error times this, okay? So the new factor, so what I really need to calculate now is AV, so this thing inside here is AV prime times V error prime, and that's going to be equal to R1 plus R2 over R0 plus R1 plus R2 times Rn plus R1 in parallel with R2 all over Rn times V error prime. So this thing right here is the new AV prime. I got something backwards here. I did something wrong here. Where did I foul it? Let's go figure it out. I got this. This is upside down. Scratch that. Let me see what's going on here. Okay, let's look at our notes here. Figure out what I did wrong. Test for you. Okay. Okay, so here's V in. So here's the circuit I just did, right? Here's V air. Here's R1 in parallel with R2. V air equals V air prime times Rn over. Okay. Oh. Here's where I screwed up. This, well, I got V air. I just got to replace what. There's two things I got to do. I have to do the voltage division of AV V air between here and here. Okay, so that gives me this factor I had right here. Let's scratch this for a second. Okay, let's try it again here. All right. The voltage I get here is through this voltage divider. Okay, that voltage divider gives me AV prime, as I said, is equal to R1 plus R2 over R0 plus R1 plus R2. V air, what I got to do now is change V air into V air prime, and here's the relationship for that. Okay, so I got to V air equals V air prime times Rn over Rn plus R1 in parallel with R2, okay? Where does AV go? AV is the new voltage gain. It's kind of just the Thevenin equivalent. Here's AV here. I have a new voltage divider which gets me to the output here. And so all of AV doesn't show up at the output. It's voltage divided down by R1 plus R2. It's just the Thevenin equivalent. What? The sum of AV? AV, this is the new. Thank you. Right, exactly. Right, okay, right, exactly right. So this is it. So it's AV is reduced by this factor right here. Okay. V air is equal to V air prime times this. Okay. So what we need to end up with then is we have AV prime times V air prime is equal to R1 plus R2 over R0 plus R1 plus R2 times Rn over Rn plus R1 in parallel with R2. Okay, so what's all this about? So what's happening is we apply a voltage at the input. We don't get all the voltage at the output here because we're reduced by this voltage division on the input. We apply a voltage at the input. We don't see all the voltage at the output because of this voltage divider associated with this voltage divider at the output. So we get our basic amplifier gain is reduced by 2 factors. Okay? All right. So now we have T prime is equal to AV prime times F. Yeah.
But where so V air go?
Pardon?
In your equation, the next page, on equation like AV prime times V air prime, it shouldn't be like some
AV. I forgot the AV.
How about VE? There should be some factor of VE AV times VE.
This is, there we go, right? This V air, I substituted for, here it is, right? High order math here is getting me. Okay, so right, AV prime. AV prime we agree is equal to R1 plus R2, this voltage divider times AV, the old AV. There it is, R1 plus R2 times the old AV, okay? Let me get, times V air prime. V air equals V air prime times Rn plus R plus 2. I replace V air by this, and I get V air prime times that, okay?
But then, like, if you look at the circuit, actually, like, what is showing on the output should be the gain times what is the difference in the input, right? And then the input is V air prime now, but like, how come we still like using the AV times V air?
Because this was the, okay. First step, okay. Here's AV times V air. This is our original case. Let's do step 1. Let's do 2 steps, okay. So the first step on the output, this is AV times V air, right? R1 plus R2, and this is R0, and here's VO, okay? So let's replace this, okay, with a Thevenin equivalent of this thing. And this, the replacement of this thing is going to be the parallel combination of these two things. So this is R0 in parallel with R1 plus R2 and an AV times R1 plus R2 over R0 plus R1 plus R2. All right? So these two things are equivalent. Okay? All right? This is just the Thevenin equivalent of that. Okay? Those two things are equivalent. I'm calling this now, and this is times V air, right? I'm calling this AV prime. Then I have to find an equation for V air. V air is equal to V air prime times Rn over this thing right here. So I substitute V air equals V air prime times Rn over Rn plus R1 in parallel with R2. And I get the new value of, so then I call this, I guess I should call AV double prime. So there's kind of, well, it's AV prime times this thing Rn over Rn plus R1 in parallel with R2 times V air prime. So we can call this AV double prime, right? Okay. Which is equal to AV double prime, oops, I guess is, so AV double prime, just to get that, is equal to this whole thing here, right? R1 plus R2 over R0 plus R1 plus R2 times Rn over Rn plus R1 in parallel with R2. And then T prime is equal to AV double prime, which includes the input and output loading, times F. Okay. So now, let me recapitulate what happened here. We started off with a series shunt network. We have loading at the output, gives us one factor, this one. We have loading at the input, gives us this factor. We have a new output resistance, R0 in parallel with R1 plus R2, and we have a new input resistance, Rn plus R1 in parallel with R2. So that's our new basic amplifier that we have right here. So this is AV double prime, okay? Then we can just plug back into our old formulas, and we've got all the input and output resistances. What's happened is AV has been reduced, right, by this voltage divider. I mean, this voltage division that we just did here is reducing our basic amplifier gain. Therefore, our loop gain won't be as high, right? So it's reducing the effectiveness of this negative feedback. Okay. Blank stares. Any questions about that? I'll do an example right now. I'll do an example. Maybe I'll make it easier. Let's take a break for 2 minutes, and then we'll do an example, and it'll make it all crystal clear. Sorry about following up in the math there. Yes.
So it doesn't need to be right here. Where's the other one? Anyways, I thought it has to be.
This one.
So if you now your new input was now your new input was VE prime. Oh,
Right.
here. Yeah. Yeah, this one right here. VE double prime, VE prime.
So AV without the prime, is that before voltage division or after voltage division? That's
AV without the prime is before voltage division.
before.
AV with the prime is with the voltage division.
How come we have this statement? Isn't it supposed to say AV prime is equal to this?
No.
What's happening?
This is the new V air, right? V air prime. Right? And here's V air here. So V air, this one here is going to be equal V air prime with this voltage division.
I thought V air prime already includes the voltage division.
No, under the output. This is the voltage division at the input side.
You're saying VE prime is your new VN kind of.
Yes, absolutely. See, all the input, V air shows up right there, right? But what I put across here doesn't all show up there, just a part of it does. Just part of it's lost across down here.
So if let's say we ignore the loading, then the input is V air.
Yes, V air would equal V air prime then.
Okay. And then once we put in loading, the V air prime is.
I want to get to where it's this voltage here. The Vn is what I want to use as my input to my basic amplifier. So how do I do that? I got to change two things. I got to change how it's dependent, and I got to change how it looks over here, right? And it's being applied across all of this resistance, not just across part of it.
So V error has to be equal to V in here then?
Yes. V error prime.
So right now you want to calculate AV prime times VA prime, right?
I want to no, I want to calculate all of this. That was the AV double prime. I want to have this whole expression here, because this is the expression of here, right?
But right now you have AV prime equal to this, and you want to calculate AV prime times VA prime.
Right.
Okay.
So I had AV prime times V error. So then I had to replace V error, and this is V error, right? And then I called this whole thing AV double prime.
Okay. So AV double prime. What's the
T prime is that's including all of these loading effects. It's a new loop game with input and output loading.
Why don't you just calculate AV prime times VA prime? Because right, you have that. I think you have the one that is with this kind of circuit, but you don't have the load there, so you call this as VA prime. And
Let's look here. Look at this one. Okay, right now.
So VA prime is from here to here, right?
Yeah.
Okay.
I'm making a new basic amplifier, so I got to include all of this stuff. Here's a new V in, here's a new V out, and I got to change this because I got some voltage division going on inside this little network right here.
Okay.
Yes.
You did the frequencies.
Oh, yeah, did you?
What is this little?
Yeah, what
is
this
Well,
what they're talking about?
That's what I was talking about. Yeah, right.
So is this
It's a little zero.
This is like does this introduce this?
As long as you can explain it. This came. You have some feedback going on in your output.
Yeah.
Yeah.
Well,
That's a zero there.
So like this is a zero and that's an.
But then we don't know how to calculate the location of zero, do we?
In that case, how do I explain? Is it possible to actually hand calculate the DVD?
Yeah, you should be able to. I don't know. It'd be tough.
Calculate zero. Can we do a frequency sweep on the output stage itself and use this whatever?
Yeah, try looking at. See if just narrow it down. If you could do that, that'd be good.
So that's good enough. If we can just
Well, then maybe you can analyze it from there, right? Do some small signal analysis. Maybe you can figure it out.
So at this point we should know enough to be able to do small
Yeah.
signal analysis and figure out where the zero is. So that
You're not going to learn any more.
feedback.
You're not going to learn any more that'll help you.
When you say small signal analysis, do you mean to find a transfer function?
Simplify it as much as you can. Get it right down so you don't have a
And then
cubic.
try to do find the
Now,
transfer function for the feedback.
Yeah, remember I did that a couple times for class, right? I solved that zero, and if you could find that, that'd be really neat. That'd be really good.
But if we can't, then we shouldn't use it.
You should really explain it carefully. Maybe if you do lots of analysis around it, break it up, it might be good too. Yeah. Include it. That's what that big discussion I had at the beginning about. That's what that was all about. So there's lots better circuits that aren't so huge, right? And that's how I can't really penalize you for not doing that really simple circuit, but it's not a good circuit. Oh yeah, yeah, oh yeah, yeah. It will. Oh sure. No, that's just a gate that turns off, right? Yeah, right. Okay, let's start again. Let's do another series shunt circuit. Okay? With all our knowledge now about series shunt. Well, let's do another circuit. And you tell me what kind of feedback it is. You'll take a good guess, I think. Ah, you got it right. Okay. Okay, as you already figured out, this is series shunt feedback. All right, now, since you figured it out, why? Where's the summing node? Where's V error? The way to figure out these feedback networks is try to figure out where that summing node is. And the summing node is that node where you take the difference, right? So we have this A coming in, we have an F coming back. This is our output, and here's our input. And here's V error. Try to find this error. If maybe it's a difference of current, or maybe it's a difference of voltages. Here, since it's series shunt, it's a difference of voltages. So where is V error? Where's the feedback? So it's kind of, these single transistor circuits are a little tricky. They're actually trickier than multiple stages because it's all kind of embedded together here. But I claim that the error voltage is being generated right here. Okay? We can redraw this circuit so it looks like this. And let me do this. Where is it? If we redraw this transit, so here's our common drain circuit. I redraw it in the form we've been talking about. So here's V in, here's V error, the gate to source. Here's the feedback voltage right here. So this is the feedback right here. It's connected to V out. So the feedback voltage V out is connected to V out. So what's our feedback factor? If V feedback is directly connected to V out, the feedback factor is 1. Okay? You can sort of see here's the output, here's the feedback, here's V out here. I connect to RS. Here's RS to ground. I'm also using the fact that we have, in this circuit, the GMB of this thing right here, and that's a current source, right? This direction, GMB times V out, right? Because V out is equal to VS for this circuit. So I've used the old replacement of, this is GMB, of a current source dependent on the voltage across it by just another parallel resistor. Okay? So I got rid of that. The other current source, GM times V error, I can't replace, okay? So it's really a dependent current source. So this, I claim, is the same circuit, right? I just got RS in parallel with this GMB, replacing that dependent current source. There's R0 of the basic transistor. Here's GM times V error. V error, I mean, this is, this VGS, V error, is equal to VGS, right? And we have to watch the polarity of our current source here, right? And so V error is equal to V in minus V out, okay? All right. And this node right here is VS. This is the source, right? So the current source goes into the source, right? So it's going into the source. So I flipped over the dependent source here, but there's still an R0 across it. All right? So, I mean, this has GM times V error in that direction, but notice the current source is into the source, and here's the source up here. The drain is grounded, so this is the drain right here, right? So that's why this current source is flipped upside down. Okay, so do you buy that this circuit here is the same as this circuit? Anybody doesn't buy that? You don't buy it. Okay, all right. It's a little tricky because I'm breaking up this transistor. Don't freak, because generally it won't be this tough to do. I'm doing this because it kind of shows you. I remember early in the year I said the reason that the source follower has the answer it does is because of feedback. Now I'm showing you the feedback that's inherent inside a source follower. Okay? So just I've flipped over the small signal, because this is the source and the drain. Usually we draw it the other way, right? Notice that the output here is being taken. It's being subtracted from the input. Here's the input. Here's V air. So it's good old series feedback. And this node to ground, from V out to ground, here's V out, right, is RS plus that dependent source on the body effect. And since there's the drain, and since V out is equal to VS, and VB is grounded, I assume here, I get a dependent source dependent on the voltage across it, so I just replace it by a resistor. Okay? All right. So here's our circuit. Here's our feedback network. Our feedback network starts here, ends up here, and this is what it looks like. V out to V feedback. So now what I want to do is include the loading effects of the feedback network on the basic amplifier. The basic amplifier is the upper part here. This is the feedback network. So I want to create a new network now that includes the loading effects of the basic amplifier. Okay. Looking into this direction, this is the loading on the output of our basic amplifier. What do I do to this side? Well, that's what it tells you, right? Series, it's open. So I open circuit this side when I'm looking from the output. So what do I see? I see, looking from the output, I see RS in parallel with 1 over chi times GM. Looking from this side, what do I see? Well, shunt means short, right? So I short this side. So looking from this side, I see a short circuit. So the loading, looking from the output of the feedback network towards the output of my basic amplifier, I have to short this. So I see 0 ohms looking this way. So my loading effects is a short. So let's redraw that. So here's the short, looking from the output, looking this way. And looking this way, I see RS in parallel with chi GM, because this is open. I see this in parallel with this. So this now is my new basic amplifier, and this is the new feedback with the output and input resistance of my feedback network. Okay? Now I need to redo what we just did. I need to include this with my basic amplifier and this with my basic amplifier and include the effects of loading. Well, notice the short on the input side means there's no voltage division going on like I had last time. So V air equals V in, which equals V air prime, right? And this is V air prime across here. There's no, since this has a short here, there's no loading on the input side. On the output side, I have R0 in parallel with 1 over chi times GM. This is a current source right now, right? So I'll calculate the new equivalent circuit, and well, I did it here, but so let's do it. Let's calculate the new voltage. What I want to do now is take this circuit and calculate a new basic amplifier. I want to calculate a new amplifier that has a V air prime coming into it. All right. I want to have a new RO prime, and I want to have a new AV prime. All right. And this goes down to my feedback network. All right. Well, I guess which RS in parallel with 1 over chi times GM. Scratch that. And then this shorts out. Okay. Whoops. Scratch that. Let's try again here. Okay. I want to do a new basic amplifier. Let me just do a new basic amplifier. So here's our V error prime. And I want to have a new R out prime, and I want a new AV prime times V error prime. Okay? So this is my new basic amplifier that I want to create. Okay? So what is AV prime? Well, I have to have a voltage. I have to calculate. This is a current source here, so I have to calculate the voltage here. V out will equal to GM times V air times R0 in parallel with RS in parallel with 1 over chi times GM. Right? So I'm just taking this current, and this resistor is in parallel with this resistor, so I'm just calculating the voltage at this point. And that's all times V air. But V air equals V air prime, so I can easily replace this. So V out is equal to V air prime times GM times these parallel resistors. Okay, R0 in parallel with RS in parallel with 1 over chi times GM. Okay, so this here is my new AV prime, or AV double prime actually, for my last notes. Okay, so now, so here it is here. So AV prime equals GM times these parallel combination. F equals 1. Remember, our feedback network was just this, right? So F equals 1. So T prime equals AV double prime times F, which is equal to this AV double prime, and AV double prime is equal to this. AV double prime includes the loading of the input and output, right? So that doesn't confuse you there. AV double prime equals AV prime in this case. Okay, so here's my new loop gain with the reduction because of the loading at the output. What's our loop? This is now here we plug into our formula. So this is our old standard formulas. AV, the closed loop gain. This is the loop gain of the whole with the feedback in it. This is the loop gain of the real circuit with the feedback. So it's 1 over F times T prime 1 plus T prime. And T prime has the loading effects of the output of the feedback network. F is equal to 1. So I end up with 1 over F times T prime over 1 plus T prime. That equals GMRS over 1 plus GMRS times 1 plus chi. And doesn't that look familiar? It should. I hope it does, right? That's the old formula we had. We calculated exactly using small signal analysis for the source follower gain. So we got this by going through this feedback network analysis now. And remember, you think about source followers. Their gains are nearly 1. Why is their gain nearly 1? Because the feedback is unity. It's a series shunt feedback network with F equal to 1. And if the loop gain is high enough, right, if loop gain is high enough, then for a feedback network, the gain is approximately 1. What happens if the gain's not high, real high? Well, that's the case here. If the gain is less than 1 in a source follower, that's because the loop gain's not high enough. Okay? And what's killing the loop gain here? What's killing the loop gain is this chi times GM. Right? RS is plenty big usually. It's the chi times GM which is making the loop gain small. So that's when we end up with that 1 plus chi in the denominator, because that's the loading effect on the loop gain is causing our loop gain of the source follower to be reduced, which is getting us a gain less than 1, which would come if our loop gain was high enough.
Question. Can you go back to one slide before this? Page 46. Yeah. Where did you see the open and the short in this graph? Like,
I've already included it here, right? There's one before this that I did the open and short stuff. Here's I did the open and short stuff, right? So I want to break. Here's the feedback network not a two-port form. I want to turn it into a two-port form like I have here. So looking from the output, this side, series shunt. Shunt's short. It's a voltage source. Voltage source, ideal voltage source is a short. So I short this side here. So from this side, it looks like a short. So from this side, it looks like a short. I'm looking the other way. I look into here. This is an open, so I see just that resistor. I see just that resistor. And there's a feedback in here. I should include one. This doesn't have everything in it, right? This should have, what I should have in here is the dependent. F times V out. So I'm missing that. I was just showing the loading effects, but this is now the complete two-port with the feedback factor in it itself. And that's F times V out. Right? So this is the full two-port. I was just showing, without that, I'm just showing the loading of the two-port feedback on the basic amplifier. Okay? So here was our AV, approximately equal to 1, because F's equal to 1.
Is that the open loop gain, or?
This is the closed loop gain. Closed loop gain with the feedback.
How do you see that it's open or closed?
Because this formula is the closed loop gain, right? This is the one we calculated when we closed the loop, and we calculated, remember, you look back in my notes, right? Remember how we got that? We took this circuit right here, we calculated V out over V in. That's the close with the feedback is the closed loop gain. And with this circuit right here, I calculated this value right here, this 1 over F times T plus 1 over T. And that's the closed loop gain, because that was with the feedback in it. The open loop gain is just the amplifier by itself. The thing we're doing today is we're including the loading effects of this circuit on the basic amplifier, because that amplifier will be reduced. Then what we do is we treat the feedback amplifier as being ideal, because we've included loading effects inside the non-ideal input and output resistance of the feedback amplifier. We've included that inside the basic amplifier. Okay, so I've said all the words now that are confusing and hard to understand. Okay, now we just got to work on understanding it, right? There's no new things coming now, okay? So you've got it all. All right, so now let's try to understand what I'm talking about here, right? All right. You get the procedure? So here, let me just go through the procedure. I calculated, assuming the feedback amplifier was perfect, no loading effects. For a voltage input, voltage output, it'd be ideal, open circuit input to the feedback amplifier and short circuit output, because that's voltage in, voltage out, right? Then what I did was I calculated a bunch of equations, these things right here. Then I went back and I said, okay, feedback amplifier is not really ideal. It really has a finite input resistance, which is going to load down this output. It really has a finite output resistance, which is going to make a voltage division on the input side. I included the effects of that loading and created a new basic amplifier that included the effects of the loading of this feedback amplifier. So then I got a new set of values. That was these AV double prime business and this new R out prime and this new R in prime. Then what I say is I can then include, using these new values, which are the new degraded values of the basic amplifier, I can use my same old formulas that I had before. I've taken the non-ideal effects of the feedback amplifier and included them up into here. What I could have done, I could have redone all these calculations with the R in and R out of the feedback network and the AV and all this stuff up here and have a new set of equations. But my strategy is to say, well, we'll just figure out the degradation of the basic amplifier and then go back into our old equations we had before. Make sense?
I know you went over this last time, but can you explain the looking in is shunt is short, and then looking in open is series?
That is probably one of the hardest things to figure out about this whole thing. What's going on with this shunt and short and series and all that stuff? Okay. The way to think about it's two-port analysis, right? let's remember how we did our, if I have any arbitrary circuit, okay, and this is an output and this is an input. Remember when we first started the year, what did we do with the, when we calculated the output resistance of this thing, what did we do to the input side? We set it equal to 0. We shorted it. That's all I'm saying we're doing right now. Okay, I'm saying, well, yeah, okay, so when calculating the output, we short the input. The output of the feedback network's looking is this side, right? Because the circuit's going this way, right? So you have to flip yourself around. So this is the output of the feedback network, just like this is the output here. I short the input, and I see a short, right? So right? This the circuit signal's going this way here, and signal's going this way here, right? So I'm shorting the output here. I'm shorting the I'm looking on the input side. Okay, when I look on the output side, I short the input. When I look on the output side, I short the input. Yeah.
Doesn't it change with series or shunt? So,
Right.
But then the
Okay.
2-port stays the same.
Okay, okay, let me finish this up. Okay, so you buy this one now. So now, looking at the inputs, looking on the input side, this is the input. What am I doing here? Yeah, so when we try to calculate the input resistance on our old 2 ports, that was from this side, we open circuited the output, right? So for our feedback, looking on the input side, we open circuit the output, just like I did before, right? So, okay. All right. Now, what happens if it's not current? This is voltage. What happens if I have this case? Oops. Let's say I have an I in. Okay. So it's a current input, voltage output. This is an R. This is a transconductance. This is I in, right? And this is an R or an AI. Let's call it an AR. This is a trans resistance, right? Times I in, which gives us an output voltage. So we have to calculate. So this is I in. We have an input current coming into this network, okay? The gain of this thing now will be a trans resistance. Will be AR times IN. This will be RO, and here's an output voltage. How do I calculate, if I give you a network and I want to calculate AR and R0 and RIN, how do I do it? Well, the way I do it, if it's a current input network, all right, IN, when I'm calculating the output resistance, what do I do on the input side? IN is our independent current. We set it to 0. Setting a current source to 0 means I open circuit the input. Okay? So for a current input, I open circuit when I calculate the output resistance. This still has a voltage output. So when you have a voltage output, you look for the input resistance with a voltage output, you open circuit it. Right? If I had a current output here, let's take that case, current output. Let's say it's let's say I had an I in, and this is an A sub I is the current gain this time, and here's an I out. Oops, and I have a resistor in parallel now, right? This is R out. How do I calculate R out? I mean, what do when I calculate, I'm looking at I in, and when I calculate R in, what do I do with the output? Open circuit or short circuit it? You short it, right? Because it's a current output, right? So you have the ideal output. So you short the output to figure out the input resistance. When you're figuring out the output resistance and you're looking back into the network this way, what do you do with the input? You open circuit it, right? Because you set the independent source to 0. So it's the extension of the voltage in, voltage output to current and currents now we have to worry about, right? So any network now, when we do this two-port thing, we have to figure out, is it an input current or an input voltage, an output current or output voltage, and we have to do the right things with it. I think I said, if you remember back early on, I told you one of the most confusing things about this feedback is going to be exactly what I'm talking about right now. And it's probably confusing right at the moment, right? But just what we're doing now is we're extending to two ports with currents in and currents out, voltages in, voltage out. So there's 4 combinations, and you got to sort of think about that.
I have a question.
Okay.
If on this project, if the area is one of the spec